What if, on the top of dealing with your melting ice cream, and you suddenly realize it's electrically charged? Oops. Talk about a shocking twist. Lima couldn't resist and decided to dig deeper. He picked up a perfectly symmetrical cone with matching height and radius and double checked it and handed over to Mr. Cloud. Mr. Cloud arranged the cone with electrostatic spraying and creating a uniform surface charge. Uniform surface charge occurs when the charge is evenly spread across the surface of an object, whether it's a circle, triangle, or cone, or any other shape. Among the various methods to achieve this, electrostatic spraying is particularly effective. In this technique, a spray gun filled with charged liquid is used to coat the surface. As the charged particle hits the object, they stick and create a uniform layer of charge by inducing an opposite charge on the surface. Now, let's dive into a bit detail about surface charge density, symbolized as sigma and pronounced as sigma. This represents the amount of charge per unit area on the surface. And if you want to find out the total charge on the object, all you need to do is multiply the surface charge density by the total area of the object and then set out to calculate the potential difference between the cones, tips, and base, VA and VB. After some serious number crunching, Mr. Cloud discovered that there's a potential difference between the 2 points. But this isn't some dry physics facts. It's a peek about how charge spread across the cone and how electric field dances around it. Think of it like this. When we talk about potential difference, we are talking about work it takes to move a tiny positive charge from one spot to another. Moving a charge from tip to base is like climbing a hill for a charge. The energy required is directly related to the stored energy in the system. But here's the fun part. This cone isn't some just any cone. It can act like a capacitor because there's a potential difference. So this device can also store energy. So Lima even set up a little experiment to measure the capacitance and stored energy using formulas which you can see on your screen. Now imagine if we can use this cone in real life application. Maybe it could serve as a capacitor in situation where traditional one falls apart. Some experimental setups where weird shapes might give you an edge. But as cool as this sound, a cone capacitor has some serious drawbacks. Unlike the smooth and predictable parallel plate capacitor, the cone shape creates a messy and non uniform electric field, and this makes energy storage less efficient and harder to control. Plus, its surface area isn't exactly designed for maximum capacitance, so it doesn't store much energy. So let's not forget practicality. Standard capacitors are easy to integrate into circuits, they are reliable and fit neatly into electronic devices. But this cone, its odd shape and complex charge distribution would be a nightmare to use in most electronics. So, in the end, this melting cone wasn't just a sticky mess, it was a glimpse into the creative side of physics, where even the most ordinary objects can reveal extraordinary principles. Thank you for watching. Subscribe for more.